Welcome to the Compendium of Knowledge, a living library of ideas, values, and thoughts, meant to spark curiosity, open our minds, and help us see the universe with greater depth and wonder. Today, we are honored to be joined by Dr. Mather, who was awarded the 2006 Nobel Prize in Physics. Dr. Mather is best known for his leadership with the Cosmic Background Explorer mission, which helped confirm the Big Bang Theory by measuring the faint afterglow of the universe's birth. His work turned the origin of the universe from a theory into a proof, showing that everything began in a small, blazing moment, and that the universe has been expanding ever since. In simple terms, Dr. Mather helped humanity answer one of its oldest questions: where did everything come from? By listening to the universe's earliest light, he turned the cosmos itself into evidence. In recognition of the impact of his work far beyond physics, in 2007, Time magazine awarded Dr. Mather as one of the top 100 most influential people in the world. Dr. Mather is a senior astrophysicist at NASA and the senior project scientist for the James Webb Space Telescope, continuing to push the boundaries of how far and how deeply humanity can see into space and time. Dr. Mather, it is an honor to welcome you to the Compendium of Knowledge.
Well, thank you, Aaron. Glad to be here with you.
So, to start off, for a young audience, could you explain in simple terms what you discovered that led to your Nobel Prize and why that discovery changed the way humans understand the universe?
Yes, sure. The measurement that we made was a precise measurement of two things. One is the spectrum of the cosmic microwave background radiation. This is the remnant of the heat of the early universe. So it fills the entire universe today, but it's not as hot as it was. So we measured the spectrum, which is to say how bright is it at every different wavelength. And it matched exactly with the predictions of the expanding universe story. We also measured a map showing how bright this radiation is in every direction. And there are hot and cold spots in this map, which explain how come we exist. Without those spots, the universe would have expanded smoothly and there would never have been any galaxies and stars and planets and people. So that's why it's important, and we can tell you a little bit more about how we did it later.
Great, thank you. That's very interesting. And also, as you were saying, your work showed that cosmology doesn't need to rely on guesswork or philosophy, and that the universe's origins could actually be measured and tested. But before all this, I begin to wonder what originally motivated you to explore the science and the cosmos, if not for a Nobel Prize?
Well, I think I was always a curious person. When I was very small, I am told that I started removing all the doorknobs in the house. When I was 6, my dad told me that living things are made out of tiny cells with chromosomes that govern our fate. And there's, of course, evolution related to all of that. So I got my attention. And I grew up in the countryside where I could see the stars, and astronomy was exciting and still is exciting. So I got opportunities to pursue this along the way. And I thought for a while I'll be a physicist. And then I'd want to be an astronomer, and then I got opportunities to do this kind of work, so I said yes. So those opportunities turned into magic. So here we are.
Wow, that's beautiful. And in your entire professional life, if you had to give one lesson, one thing you think would be most beneficial for the youth of today, what would that lesson be?
I would say ask for help. It does two things. So one is it gets you help, and number two is it says, I am worthy, my ideas are worthy of help. So it affects one's self-image in the world, and other people see that. So if you say what we're doing is important, and people feel it, and they may actually want to help. So that's a very important step to take.
Yeah, that's very interesting. And I feel like people today, they're often scared to ask for help, and they may think that it's for some reason doesn't make them as smart. And also, you've often spoken about the importance of reading and writing, not just for science, but for learning how to think clearly, persuade others, and communicate big ideas. How have reading and writing shaped your own journey as a scientist, and what advice would you give young people who want to use words to change minds and possibly even move the world?
Oh, well, my goodness. Of course, the world does move itself. There are many of us here trying to move the world in different directions, but if we are able to think logically and write that down in words, it helps us persuade people, it helps us persuade ourselves, and even discover the truth. So, writing is a process for me of trying to set out ideas in a logically consistent fashion, a persuasive fashion. And sometimes I find that what I had in mind isn't correct. So, writing is a way of pursuing the truth as well as trying to explain it. And so, also, of course, if you want other people to do what you have in mind, then it's good to be able to say why and show the benefits. What's in it for them? So, all of those things relate to communication, and it's not just reading and writing, but reading and writing is a good place to start.
And in your life, how have you developed those skills, reading and writing? And say there are some young people today who are possibly more shy, or they feel that maybe, I guess, STEM is just their focus. I guess, what method would you give to them, and how do you think they could develop their skills to
Oh, well,
communicate?
my goodness, there's no substitute for just doing it. Um, I remember the first public presentation I gave about the Cosmic Background Explorer. I was unprepared and terrified and perspiring. And I said, in the future, I'm going to prepare much better. Um, but also, it was actually quite hard for me to learn to write well. But the only solution to do that is to keep on doing it, and think about every step along the way, and until you can get good at it. Same with public speaking. Same with every kind of difficult skill that we don't have, but we can grow. So just do with some intention to learn. So there's a way to learn how to do these things, and we just have to find that.
Yes, definitely. And also, my personal impression is that Nobel laureates have always had one thread in common, which is the desire to contribute to something bigger than themselves. Now that you have received this recognition, what are you doing to continue inspiring and empowering young people today?
Well, I do what I can by talking with people and trying to explain the beauties of the universe and the mysteries of the universe, and to say, and yes, we can find out some more about them. So, for me, one of the great, not only in astronomy, but in life in general, is where did life come from? And I'm going to talk a little bit about that later with some presentation material. But where does life come from, and what does it mean? And for a long time, I could not answer those questions at all. Now we have a little bit of the scientific basis for as part of the answer, but I think we are now at a place where we can make a lot of progress by discovering more things. And of course, we're also on the crest of making computers that act a lot like people in good and bad ways. So brings the philosophers into the question of what does it mean. Um, so there is a kind of experimental approach we can take.
Thank you. And lastly, in your life, of course, you mentioned how you love physics or physics and the stars at a young age. But for a young person today, how can you go from someone who loves physics as a child to go into it such a deep level and make such big discoveries and possibly even win a Nobel Prize? How did you do that in your life, and what advice would you give regarding that?
My goodness, well, it was not done with a plan. It was done by being in the right place at the right time and saying yes to opportunity. So, when I was finishing, when I was in graduate school in physics, I thought I wanted to be a theoretical physicist. I wanted to be able to discover those equations like Einstein could do. Um, and they said to me, "Well, are you rich?" Because there were no jobs for such people. So, okay, so find a thesis project, find somebody who's doing something interesting. And I said, okay, these people are going to try to measure the cosmic microwave background radiation. Well, I'd like to try that. So I did. So my thesis project was a balloon-borne payload to measure the spectrum of the cosmic microwave background radiation. Well, it did not function correctly, so I had to write a thesis about an incompleted project. But I threw even as we were doing the project, I said, and I think people knew all along, if you could have done this measurement from outer space, it would have been much better. So 6 months after I turned in my thesis, I was at NASA, and I did not expect this, but NASA said, we want proposals for new satellite missions. I said, idea. We could do what we tried to do before, only better. And my bosses said, yes, we know what to do. We will call up our friends and we will write a proposal. So this is all of us saying yes to opportunity. And we didn't know if it could possibly work, but we said, well, it's worth trying. So that's how it grew. Eventually, NASA said, yes, it's a good idea. We'll give you some money to figure out how to do it. Later on, they said, it's so good an idea that we're going to really do it. And then there was a lot of difficulty along the way. But you can read the story of it in the book. The book is called The Very First Light by John Boslow and me.
Wow.
So it's in a book, and it gives you some sense of what it takes to do a giant project. So it's 1,500 people took it. It took 1,500 people to do that project. So it's not a small thing. But how did you get 1,500 people? Well, the idea was important, and the idea that we could discover something worthwhile, possibly revolutionary, was important. And so people could see that it was worth doing.
Thank you, Dr. Mather. Your story is inspiring, and now we would love to delve deeper into your discovery. As part of your learning module, could you help us understand what we might call the story of the universe itself? How faint traces of ancient light, when measured with extraordinary precision, can come together to reveal where everything began.
Okay, well, we'll give it a try. I do have a presentation for you. What I now want to do is explain the results of the Cosmic Background Explorer and the Webb telescope a little bit in context with many other discoveries. So on the cover sheet here, what you see is a picture of the James Webb Space Telescope, which is the project I did after the Cosmic Background Explorer, and also the jobs that I had. I was the senior project scientist from 1995 to 2023, and now I've handed it off to other people who are running the observatory beautifully. And just for the record, it is in beautiful shape. It is taking great pictures every day. So, but we'll go along to the beginning of the universe questions now. So, just a little history, though. This is where I grew up. There's a farm on the left-hand side which was devoted to research on dairy cows. How do you get more milk and better milk from cows? So there's a chemistry lab in that barn, and there was also the home for 20 bulls who were the ancestors of many, many cows in northern New Jersey. So it was genetics research as well as nutrition. And so that's where I lived, and the sky was blue and clear, and I could see the stars at night, unlike where I am now or in the center of London where you can't see the stars much. So it was a fascinating place to be. That's my family on the right-hand side. My dad was the scientific researcher working on the animals. My mother was a school teacher, and her father was a scientist also working on penicillin. And there I am with my sister behind them. So we weren't very old at the time, but it's also a moment to point out how much has changed since those days. This was before the space race, before the Cold War, or maybe at the beginning of the Cold War that we had with the Soviet Union. Just everything has changed in our world since that time. So I always wanted to know, how does everything work? So I'm now able to summarize some of the steps towards that. We have 6 that I've tabulated here. And we have the mathematical things where we can work out the logical consequences of something that we agreed to start with. So we're quite certain of the answers to most questions in mathematics because it's deduction. Then we have what we call the exact sciences, like many parts of physics, where you say, well, I have my equations and I can tell you what's going to happen. And the beginning of that was Isaac Newton with his equations of motion that we could test on the solar system. So now we have an extraordinary degree of capability in that area, and those are exact sciences. You can be very sure if your model matches the basic idea that you're going to get the right answer. Then we get to much more complicated systems like the real world, where we say, well, we know what the principles are. We know that the laws of physics underneath apply, but it's too complicated to get the same answer every time. So there are general principles, there are chaotic results, and you cannot predict very far into the future. So we're about to have a giant snowstorm here, and honestly, even though it's a few days in the future, we don't know what's really going to happen. We just know something is going to happen. Coming back a little farther into time, we'd like to know the origins of life. Darwin speculated about that, and he couldn't possibly know. He might have been right, but we don't know that yet. Anyway, it's something we are making progress on. Then we get on to as we get to the real complexity of our world, of course, we have in our brain boxes an extraordinarily powerful supercomputer, a bio-supercomputer, but it is really not like the rest of the computers that people build. And it programs itself as it goes, and it's alive. So that's pretty tricky. Finally, then we get to the meanings of things, what I call the world beyond science, which is basically everything that matters to people. So this is what I like to think about as what makes science interesting in the context of human life. So I'm stepping back, however, into the history of cosmology. This is the first quantitative cosmology that we've had. Back in 1929, Edwin Hubble drew this graph. And the graph shows each dot on the graph shows a galaxy. A galaxy is roughly 100 billion stars held together by gravity. And the dots show how fast they're moving away from us compared with how far away he thought they were. And you see two really interesting things here. One is that almost all of them are going away from us with rather large speeds. And number two, the speed is approximately proportional to the distance. So how does this happen? Number one, it says everything is rushing away from us. How long does it take for that to happen? Well, divide the distance by the speed, and you get the apparent age of the universe. Now, you have to adjust it a little bit in case you think the rate of expansion is changing over time, because it does. But at any rate, roughly speaking, there's the age of the universe. Divide the distance by the speed. And the age turns out to be, in modern measurements, 13.8 billion years. And these distances are immense. The units on this picture are millions of parsecs, and a parsec is 19 trillion miles. So this is an immense distance we're talking about. Distant galaxies are unthinkably far away. But nevertheless, 1929, the first evidence we had of the expanding universe. And by the way, Hubble's particular contribution to this was that he showed that there are pulsating stars in the Andromeda Nebula, and which proved that the Andromeda Nebula really is made of stars, as well as proving that it's very far away, and you could estimate the distance. So, by the way, this was all predictable from Einstein's equations, but Einstein did not make that prediction, so this was quite a controversial discovery in 1929. So, the beginning of the picture of the expanding universe. We now call it the Big Bang picture, which is unfortunately misleading, because Big Bang suggests something like a firecracker, a small object blowing up in a pre-existing space and time. But the picture here does not tell you that. The picture here suggests that the universe is infinite now, was always infinite, and so when we say, going back in our imagination to when the universe was young, it was much more compressed, but was never small. So this is a tricky thing in our English language. We have been deceived by the name of the Big Bang because it makes us think of a firecracker. So anyway, 1929, couple of other things happened a century ago. Excuse me. About 1925, Erwin Schrödinger wrote his equation of wave mechanics. And these days we call it quantum mechanics, but it should be called wave mechanics because it's actually the fundamental idea is that everything you see is made out of wave packets. So little vibrations of something or other in space. So we have electron waves, proton waves, electromagnetic waves, neutrino waves, a big collection of names that we give to the different kinds of waves, and little wave bundles, little wave packets act like particles, but sort of like a hurricane, a wave packet does not have a particular definite spot or a definite velocity. So we have confused ourselves by calling these quantum things and making them uncertainty questions, which actually are much more basic than they sound. In other words, uncertainties are mathematical identities in this case. At any rate, we have equations of motion for the various kinds of particles that we should be calling wavicles or wave packets. And now we know how to calculate everything. And I've given you a reference here for the students who want to get further into this to know about wave packets as the fundamental idea. Over the course of the last century, we've now made a quite complete list of the various kinds of wave packets. So I've relabeled the chart here with wave packets. We've got 6 kinds of quark wave packets. We've got 4 kinds of force carrier wave packets, gluons and photons and bosons that relate to the nuclear forces and electromagnetic forces. And there are also 6 kinds of leptons. Leptons are much lighter particles. At any rate, this has taken us about a century to work this out, and we may or may not find more particles to put on this kind of chart. So that's some of you in the audience may actually get to work on this one. This is where the current work is on at places like the Super Collider in at CERN. So don't know what secrets are hidden behind this, but there probably are some more to be found. Now, how does this happen? Well, here's my cartoon illustration. People want to know, is there really only one way this could work, or are there other possible universes? So we have made many attempts to guess the laws of nature, to say, well, here's this mathematical formula, and it predicts the way that it should be, and that would be called the grand unified theory of the universe, and we have failed so far to find it. So there's also the possibility that maybe the laws of nature are different in different parts of the universe, or in even what we call separate universes that we might never know about. So unknown, but something for you all to work on as time goes along. So now I want to show you a picture of this satellite project that made us famous. This is called the Cosmic Background Explorer Satellite. And it is still in flight above the Earth. It's about 900 kilometers up in a roughly circular orbit. And it carried 3 instruments, 2 of them to look at the cosmic microwave background radiation, which has wavelengths of a few millimeters to a fraction of a millimeter. And there's also an instrument to look at much shorter wavelengths, the infrared wavelengths, to look for the light of the very first galaxies. So this is, as I mentioned, the follow-on to my thesis project at Berkeley when I was a graduate student. And this time, of course, it worked beautifully because real engineers made it work. So we did basically 2 major discoveries on the cosmic background. We confirmed the spectrum was as predicted, and we found hot and cold spots. We also measured the accumulated infrared light that came from the first galaxies, which is still a bit mysterious. Did we get the right answer? Eventually we found out yes, because 2 more satellite missions were built to follow on afterwards and verify and measure better. And they got the same answer that we did, only much more precisely. So there it is, the equipment in outer space, still up there but not working. So here is a summary of the major results. On the left-hand side, I show a graph of what we call the spectrum of the cosmic background radiation. As you can see, the curve, which is the curve that was worked out by Planck himself, and even before 1900, I forget the exact details. Anyway, what we found is that the measurements of the sky follow exactly with the predicted curve. And the only way that could happen would be if the universe was so hot and dense that there was only one temperature. So at a time and place. So then it would expand and cool, and it would preserve this particular curve, the only change being the temperature. So when we measured that, and I showed this to the Astronomical Society, we got a standing ovation from 2,000 astronomers, because they said, finally, we know that the simple picture is the right picture. So there I am in the middle, getting my diploma from the King of Sweden in 2006. And of course, there's always a cartoon about everything. You may already be a winner of the Nobel Prize. So that's the number one thing, the precise measurement of the spectrum. Eventually, we got the accuracy down to 50 parts per million. Pretty astonishing even for us to be able to make that claim. So the second major discovery, which we announced 2 years later, was a map of the universe as seen with millimeter wave eyes. So the sky is covered with hot and cold spots. And of course, this is the result of a lot of work. We had hundreds of millions of measurements that had to be averaged together to make this map. And we also had to subtract out the interference from our local environment. Of course, we live here in our own galaxy. The Milky Way galaxy is bright. It emits light from electrons that crash into other things and also spiraling around magnetic fields. All that had to be understood and subtracted to get this map, which is the residual and which we believe is primarily left over from the earliest moments of the universe. So there it is. When Stephen Hawking saw this map, he said that was the most important scientific discovery of the century, if not of all time. So why would Stephen Hawking say that? Well, number one, if those spots were not there, then the universe would have expanded smoothly and would never have produced galaxies and stars. Number two, most of those spots we now know come from cosmic dark matter, which is a kind of matter that has gravity but does nothing else, as far as we can tell. So that's a result that's now been confirmed in many other ways. There is dark matter in the universe, which is much more abundant than ordinary matter. And it totals up to about a quarter of the entire universe is dark matter. There's a third effect in here. The pattern is affected by cosmic dark energy, which is so the cosmic dark energy is what we give the name for the current acceleration of the expansion rate. So the universe is going faster and faster every day, and we call that because of dark energy. So that affects the pattern here. And finally, if we ever understood what makes the spots, maybe we'll understand something about the processes of the very earliest moments in the expanded universe. So there's evidence in this pattern that we have not fully appreciated yet. It's not finished yet, but we have an idea that if we could measure the polarization of the light that's in these spots, we would be able to tell about gravitational waves in the first sub-microseconds of the early universe. So that's why this pattern is so important, and why thousands and thousands of astronomers and physicists have worked on this so hard, and there have been already 3 space missions, and there is a 4th one in preparation. So that's why this has turned out to be so important. But moving on from that, what do we do next? Well, as mentioned, there is the dark matter. We don't know what it is. We know that it exists. It affects the orbits of things, and it bends light. a Nobel Prize was given for discovering and measuring the dark energy in multiple different ways. There is the idea of cosmic inflation, which is a hypothetical quantum mechanical field that would cause space itself to expand in the way that we have. So it's a lovely idea. When I first heard of it, I thought, well, we'll never be able to test it. But it makes a prediction which we did not know about before, which is about how many large diameter spots are there compared with how many small diameter spots. So that was a remarkable result, and it seems to agree very well with the predictions. There's another huge asymmetry. As far as we know, ordinary matter and antimatter are exactly anti-symmetrical. So, but must be a reason why the universe is made of ordinary matter and not antimatter, and we're still hunting for that. So anyway, that's many mysteries for you in the audience to pursue yourselves, and it'll take a while, maybe centuries, for us to get the answers to these mysteries. So a few things to tell you, though. There's a possibility that dark matter has done something besides to have gravity. This is a result from an observatory we call the Fermi Observatory. And what they are doing is observing gamma rays. The sort of reddish and yellowish glow that you see in the image comes from near the galactic center, the center of the Milky Way, where we think the cosmic dark matter will be concentrated. And so if it is speculated that dark matter can annihilate dark matter by having a collision, then it might produce gamma rays of 20 giga-electron volts, 20 billion electron volts energy, which is large, but anyway, big enough that we could detect it. And the image says maybe we have. So if this is true, then it's the first detection of dark matter as a particle. So, however, of course, this is a hard observation, and so you're not quite sure, but for me, it's very tempting and promising. Let me talk about the James Webb Space Telescope for a little bit. Here is the great telescope in space. It is a successor, but not a replacement for the Hubble Space Telescope. It's much bigger. The mirror here that you see is made of 18 gold-plated hexagons, and the mirror diameter is about 6.5 meters, which is about 2.5 times as big as the Hubble telescope. It is so big that the telescope had to be folded up for launch and it went up in December 25th of 2021. It is protected from the heat of the sun by the 5-layer umbrella. We call it a sunshade there under it. So the purpose of this was to open up a new domain of astronomy, to pick up infrared light from the most distant stars and galaxies and from things closer by that are too cold to emit their own visible light. So there it is as we imagine it to be in outer space. It's been operating for 3.5 years. Is that right? Maybe from 4.5 years now. So very powerful observatory, and still working beautifully. So I want to show you just a few things that we found with it. One of the great hopes was we would find something that nobody had ever expected before, and we have. Here is a new kind of object we call them little red dots. And we call them little red dots because they're very compact. They're about 1% of the size of the Milky Way. There aren't any left, as far as we know. These formed about 1 billion years after the Big Bang. And they're extraordinary dense objects. They spin extremely fast. And we have two kinds of leading explanations for them. One is that they're supermassive stars inside, maybe 5,000 times the mass of the sun. There could also be that there are one or more black holes inside that are somehow blanketed so thoroughly that you can't see them. and all you can see is the residual light coming out in the infrared. So this is a wonderful discovery, and we do not know what they are. Many people tell you that they know what they are, but we're not really sure yet. Another example of this, here's a theoretical prediction of, it's a hydrodynamic simulation, imagining a primordial gas cloud forming the first generation of stars. And the hint from this computer simulation says the turbulent motion was so intense that it would prevent ordinary stars from forming until the density was so high that stars of order 30,000, 40,000 times the mass of the sun might form in that cloud. And if that could happen, then the first black holes could be formed that way, maybe with 30 or 40,000 times the mass of the sun themselves. We have already seen an object that has an extremely high nitrogen abundance in the debris that comes out into the gas. So that is as predicted for masses for stars of a few thousand solar masses. So this might be part of the real story. Don't expect certainty, but this is a very tempting idea. So maybe this is what's inside the little red dot. So closer to home, we've been looking at places where stars like the sun are being born. This is a place called the Pillars of Creation, which we knew about many decades ago from Hubble Space Telescope. The Webb telescope can see the infrared light. And what you see here is gas clouds that are a few light years in size, maybe 5 light years in size. And they are shaped by a wind blowing through space. The wind comes from the energy of brand new stars that are liberating huge amounts of energy, very, very bright, and sending out a wind, which is blowing through space and impinging on this other colder gas cloud and causing compression, causing new stars to be born. So, for instance, right a little bit in the middle, there is a little bright object which seems to be growing at the end of a dense cloud of gas. So this is a star formation laboratory, many, many hundreds of new stars being born in there, and eventually we'll be able to say, we understand how this works. Right now, it's a laboratory for us to learn how things work. We have seen a few stars being born. Here is one. This is an edge-on view of a new star being born, and you cannot see the star. It is right there in the middle, where the markings say dark lane and disk. Right in the middle, there is a hidden star. We see edge on the disk orbiting around this new star. And just to remind you, the solar system is flat. All the planets, all the big planets orbit in the same plane. And that's left over from the formation of an orbiting disk of material falling into the sun. The same thing seems to be happening in this new star being born as we speak. There are jets of material coming out the north and south poles. It's spinning, and somewhere hidden inside this dark lane and disk in the middle are probably a handful, maybe 5, 10, or 20 new planets being born there. So come back in 100,000 years, when most of the dust will be gone, and you maybe be able to see the planets then. Of course, we're interested in the planets themselves. With the Webb telescope, we are able to see exoplanets, a few of them directly, but mostly we see them when they go in front of their host star, and they block some of the starlight. So when we block some of the starlight, we can begin to analyze the planet itself. How big is it? Because of how much of the starlight is it blocking? And some of the starlight can go through the atmosphere of the planet if it has an atmosphere, and we can analyze that part and get the chemistry of an exoplanet. So we've got this for many, many exoplanets, but so far none of them are like Earth, which is not very surprising because this is a technique that doesn't apply very well for a planet like Earth. But at any rate, we have a method, and we have learned a great deal about other planets, and very, very interesting results. The solar system is unusual. So far, we have not seen any other solar systems shaped like ours with small planets in the middle and then big planets orbiting outside an asteroid belt. So, if we'd like to know about the origin of life, well, of course, we want to see if there's life elsewhere in the solar system. This is an image taken of the surface of Europa. Europa is a satellite of Jupiter. It was discovered by Galileo himself in 1609. Our probe was called the Galileo, and they got pictures of the surface, which we now see is covered with ice. And there are cracks in this surface that now we know. Once in a while, water jets come up from between the blocks of ice. And we have sent a new probe called the Europa Clipper to fly through the jets of water coming out from this small satellite to see if they have organic chemicals in them. So if there is another place in the solar system that could have life, maybe this is one of them. And we'll find out soon if there's any evidence. So how do we get from there to life as we know it? Well, there are many instabilities in our world. In physics classes, you might learn that things don't happen like this because in equilibrium, when everything's at one temperature, you can tell what's going to happen. It's one of the exact sciences. When things are not at equilibrium and there's an energy flow from place to place, then complexity occurs almost always. So here's a series of 6 steps, or five steps of instabilities. So first we have the cosmic inflation, as we have guessed it to be, that causes the expansion of the universe. And then that enables the elementary particles to form stars through gravitation. And so stars form, energy flows out from stars. That enables energy flows on the surface of the Earth and what we call spontaneous heat engines. So an example of a spontaneous heat engine is a hurricane. A hurricane extracts energy from the warm ocean and helps increase the entropy of the universe by increasing the energy flow from the ocean to the poles. And so complex systems nor form naturally when there's an energy flow. Seems to be a universal principle. And although we would never have been able to predict it from the fundamental laws of quantum mechanics, it turns out that organic chemistry, based on carbon and chains of carbon molecules, is obviously able to support the formation of life. How did that work? We can't tell you yet. But once it gets started, we have the incredible growth of information. So each of us has several billion letters in the genetic code in our cells. That each cell inherits a slightly different version of that genetic code, and our cells mutate as we grow. And then there's the mysterious question of what is it that reads the genetic code and turns it into instructions for our cells to do whatever that is that they do. At any rate, the unlimited growth of information through life. So that's how we get to ourselves from the Big Bang. So it's a few examples of this. On the left-hand side, we have a diagram explaining the weather and the climate of the Earth. And you can see these predominant patterns of the air flows and trade winds that we learned about in school. And the general idea is pretty well predictable. The details are never predictable. So it's chaotic. Similarly, in the center, we have a diagram illustrating the internal structure of a cell. And it's when you hear the idea of a cell, you see, well, a little blob of jello. But it's not actually true at all. It has a structure, which is we're beginning to work out. It's a mechanical structure. It has pumps, it has pipes, it has ladders, it has motors, it has valves, it has regulatory systems, it has the devices that read the genetic code and tell the cell what molecules to make and when to make them and where to make them. So all of that is completely simplified in this little diagram showing the complex structure of a cell. So people are beginning computer models of that, but it's almost impossible to do. But we have to try. Finally, then on the right-hand side, we have a rodent, which will do whatever it wants. So we get from complexity to complete unpredictability, and the essence of consciousness and life on the right-hand side with the rat. So how did this all get started? Well, no one knows, but we're beginning to guess. So we start off with a world that we're in, which for whatever reasons are not quite known, but it is habitable, meaning that it's the right temperature, the right pressure, the right size, the right chemistry for life to occur. Then something happened. Large molecules were synthesized through inorganic processes without the existence of life, and then something happened to get them together to enable them to form cells or something like cells, at which point they became able to continue to grow and reproduce, producing this entire network of millions of different kinds of living things, apparently all descended from what is called the last universal common ancestor, which does not necessarily imply that life occurred only once, only that the kind of life that we have today is descended from at least one common ancestor. So tricky thinking there, but let me refer you to a book, Is Earth Exceptional by Mario Olivio and Jack Shostak from 2025. Very new book, a brilliant book. So how is it possible that life could occur based on that original prebiotic chemistry? Something had to happen to concentrate the molecules enough so that they could begin to interact with each other. Here's an idea, which is perhaps you have a little pond and molecules occur, and then it dries out. And maybe the molecules condense onto the surface of clay or some other catalytic mineral, and they get to the density of molecules gets to be enough to be interesting, so that perhaps a protocell could occur based on the molecules that just happen to be there. So this is pretty much of a guess, but people are doing laboratory experiments to find out if this is true. So what happens then? Well, just to point out, there are about 30 billion cells in each of our bodies. There are an awful lot of other living things here on Earth, so approximately 1,000 billion cells are alive today on the surface of Earth or inside the rocks of the Earth. Somewhere here, there are vast numbers of them, and they have incredible creative forces. They solve problems every day, every minute. They have creative response to their situation. They grow, they migrate, they send out chemical signals, physical signals, electrical signals to the things around them. They extract energy in order to be able to grow and do all the things that they do. And there are so many of them that it's totally impossible for us to predict what they will do in general. But we can see that whatever it is going to be very, very unique, not repeatable, and complex beyond imagination. So in physics, we have a principle that if it's not forbidden, it's required. And it relates to quantum mechanics, and it was a sort of tongue-in-cheek version. Here in biology, I think we have a similar principle, which says that if there's no physical impossibility for some strange thing to occur, we ought to look for it, and it might be happening. So that includes all kinds of communications between different kinds of living things. So this brings us to the question of meaning. So where do you get meaning? Well, in our world, I've described for you huge complicated systems. So they're all doing things, and and each system has a function within a larger system. So in our body, we have our 30 trillion cells and our 86 billion neurons, and they all function together to make us humans. So it's going to be very interesting and different, but we can see that there is meaning for each of us agents as part of a larger whole. So that's a place for you to think about the meaning of life. This is just the beginning. This is the basis. But we all have functions and roles in our families, in our societies, and in history. So there you are, something for you all to think about. So just as a reminder, our astronaut Jim Lovell said, we don't go to heaven when we die, we go to heaven when we're born. There is a heaven, and God has given you the opportunity to enjoy the best things in life right here on earth, right now. I love what he said because it reminds us that we are indeed special, different, unique. There's nothing like us anywhere else in the universe that we know of. So I encourage you, and I wish you all the best in your further studies. We have time before the next great disaster. Thank you.
Thank you, Dr. Mather. I loved that quote earlier. And thank you, Dr. Mather, for joining us on the Compendium of Knowledge. It has been an honor to have you here with us.
Delighted to be with you, and look forward to seeing the results.